Scrolling down to the last bullet point there, investigate the types of nucleosynthesis reactions involved in main sequence and post-main sequence stars, including but not limited to the proton-proton chain and the CNO cycle, the carbon, nitrogen, and oxygen cycle. So Chris, welcome to the depth study. Thank you very much for signing on this year again. And if you'd like to take over the screen share so we could see you and your presentation.
Thank you, Matt. Hello, everyone. It's a real pleasure to be here to speak to you. So let me share my screen. That's sharing everything, so let me just share something more specific. I'll share my presentation instead. And hopefully you will all see that. If you don't see that, shout out or leave a comment on the QA and chat. So before I start the talk, I did want to answer a question from Nalim about what is the UV catastrophe, because that's a very interesting question. And it's a question that goes back to the beginning of the last century, around 1910, and before quantum mechanics. So in Ilya's talk, you would have heard about black bodies. Black body is a concept where you have light being emitted from a body of a certain temperature. An example would be the sun. The sun has a temperature of 5,000 Kelvin, and the spectrum it emits peaks in the visible. So that's why we see the sun, it's an orangey color. Now, at the beginning of the last century, physicists were trying to predict this curve, and they were using a classical theory at that stage. And the predictions from theory came up with a curve which was quite different from that observed. The curve that they derived was one in which the number of photons and the energy increased when you went to shorter wavelengths. And shorter wavelengths means you're observing in the UV. And so that's why I was given the term ultraviolet catastrophe, because the theory did not at all coincide with the observations. So it wasn't until quantum mechanics came along that a theory was available to actually predict what that black body curve looks like. And in this talk here, I'm going to show a black body from the beginning of the universe, from the cosmic microwave background. So I hope that answers Nalim's question. It was one of the, I guess, signposts in the previous century, which indicated that our theory of matter and radiation was not complete, and this led to quantum theory. Okay, so with that, I will proceed with this talk. So in the previous talk by Dilya, you would have seen the periodic table, and here is my version of the periodic table, not mine. It's actually created by Jennifer Johnson from Ohio State University, and it's one of my favorite versions of the periodic table, because it colors the elements in different colors. So you have hydrogen at the top left-hand corner, which is the lightest element, all colored in blue. Then helium to the top right, colored in blue, but also with a bit of yellow and green. And then the other elements, increasing atomic weight as we go down to the bottom right of the periodic table with different colors. So what do these colors mean? These colors indicate where the elements come from. And in this lecture, I'm going to go through the physical processes that lead to these different elements. And it's a very, very interesting story. So before we go into that story, which will start with the Big Bang, and then we'll go through stars and supernova and all that sort of cool stuff, I thought I'd just remind everyone of the elements essential to humans. Now, normally when I give this talk, I usually ask a question. Which of these elements here, which are essential to human life, is the one by mass, which is most common in the human body. And most people get the answer after a few clues. It's not hydrogen, it's not carbon. Many people think it's carbon. It's not nitrogen. It's actually oxygen. And the reason for that is that most of our body is actually made up of water. And you would recall that the chemical formula for water is H2O, so two hydrogen atoms and an oxygen atom. And oxygen's a lot heavier than hydrogen. And so and actually about 65% of our body mass is made up of oxygen. And the top six elements are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. But there's a lot of very unusual ones which you may not have heard of. So an example would be iodine, number 53 in the periodic table, which is essential. The thyroid uses this to make growth regulating hormones. Another interesting one is molybdenum, element number 42. This converts sulfites to sulfates. So if you have problems with sulfites, which usually lead to headaches, it may be that your body is a bit deficient in this particular element. So they're the ones essential to humans. So it's actually quite a large number, perhaps a surprisingly large number. Of course, there are some other elements which shouldn't be there. Lead is one of them. It has no role in the human body. And another one is mercury. These are heavy metals which we find sometimes in our bodies due to contamination and pollution. So I'm going to first go through the four elements. We're going to talk about protons, electrons, isotopes, and those sorts of things. I need to do this because the rest of the talk will refer to these things. So hydrogen is the simplest element. It consists of one proton and one electron. Recall that the proton is positively charged and the electron is negatively charged. And 75% of the matter in the universe is made of hydrogen. On the left-hand side, you'll see the symbol for hydrogen, H, and the number 1 to the left-hand corner. That represents the number of nucleons, and nucleons can be either protons or neutrons. And so in this particular case, in this simple version of hydrogen, the most common, there is one proton, and so the number of nucleons is 1. Now, hydrogen has different isotopes. So isotope of an element means that there are different numbers of neutron. So the number of protons always defines the element. One proton means that the element is hydrogen, but you can have different numbers of neutrons. So another common form of hydrogen is deuterium. In this particular case, you notice the symbol, hydrogen, and then the number 2, because there are 2 nucleons. You've got one proton and you've got one neutron. And then to the right, we've got another form of hydrogen, tritium, in which you've got one proton and 2 neutrons. And so then the number goes to 3. And you see that that is equal to 2 plus 1, 2 neutrons and 1 proton. All of these atoms are hydrogen, as they all contain 1 proton. Now, one thing you also see that some of these isotopes are stable. So hydrogen with 1 proton, no neutrons, is stable. Deuterium is stable. That means it does not decay. But tritium is unstable. Tritium has a half-life of 12 years. What does that mean? That means if you've got 1 kilo of tritium and you wait 12 years, you've got half the tritium left because the other half will have decayed. If you wait another 10 years, then you've only got 250 grams. If you wait another 12 years, you've got 125 grams. So every 12 years, you lose half the tritium due to radioactive decay. The next element in the periodic table is helium. And again, 2 protons means that it's a helium atom. And in the usual form, you've got helium-4, which consists of 2 protons and 2 neutrons. That's stable. Another form of helium is helium-3, where you've just got 1 neutron and 2 protons. And then a more extreme example is helium-2, where you've got 2 protons and no neutrons at all. And then helium-5, in which you've got 2 protons and 3 neutrons. And you will note that the 2 forms of helium, the 2 isotopes of helium at the top, are stable, whereas the 2 forms at the bottom are unstable. And the half-lives of these 2 isotopes are very, very short compared to the 12 years half-life of tritium, an isotope of hydrogen. So here you see for the 2 proton version of helium, half-life is 0.000, etc., 1 second. In scientific notation, that's 1 by 10⁻⁹ seconds. And then the helium-5 version is even less stable. It has 1 × 10⁻24 seconds. We then go to lithium. You've got lithium-6 and lithium-7. Lithium-6 has 3 protons and 3 neutrons. Lithium-7 has 3 protons and 4 neutrons. Both are stable. There's also other forms of lithium which I don't list here, but I list these two because these are the most important for the remainder of the talk. And then I'll go to the next element, beryllium. 4 protons and 5 neutrons is the stable version. There are other versions, one with 7 nucleons, so that's 3 neutrons and 4 protons. Another version, helium-8, so beryllium-8 with 4 protons and 4 neutrons. And you get to see the half-lives, 53 days for beryllium-7 and very, very small short half-life for beryllium-8. And beryllium-8 is a very important element for a number of reasons, and that'll become clear when we start talking about nuclear synthesis. So back to the periodic table. We're now going to start the story of how these elements were created. And our story starts with the Big Bang. We're not going to start right at the beginning, the Big Bang. We're going to start a few microseconds after the Big Bang, after what's known as baryogenesis, which is where the protons and neutrons and electrons have been created. So our story starts here. At that point in time, the universe consists of just these particles, plus some photons, neutrinos, and dark matter. Now, we don't know what dark matter is. We know it's around, but dark matter was certainly most likely there at that early time as well. So, as time evolves, the universe, which started the Big Bang, was a very hot, very dense state. Very high temperatures and very dense. The universe was also expanding, so as time was increasing, the temperature was decreasing. Now, the temperature is very important because for 2 protons to approach each other, you need to overcome the repulsive force of the Coulomb interaction. So each proton is positively charged. If you're going to get them to get close enough in order for the strong force to take over, they've both got to have very high velocities, and that comes from having high temperatures. So what's shown here is the chain of reaction which goes from the proton and neutron, which were there at the end of baryogenesis, and how they come together to form deuterium. Recall that deuterium has 2 nucleons, a proton and a neutron. And here, for simplicity, I've taken out the electrons. In fact, at this early stage, the universe was completely ionized, and so all atoms were stripped of their electrons. So once you form the deuterium, the proton approaches the deuterium atom and then forms helium-3. Again, you need to have very high temperatures for this to happen because this proton's got to approach the deuterium atom, which has a positive charge. And while this is happening, the universe is expanding and getting cooler. So then helium-3, another neutron comes along. It forms helium-4, so 2 protons and 2 neutrons. And then the 2 helium nuclei come together and merge to form beryllium-7. And again, here the temperature has to be high enough for these 2 nuclei to approach each other to be close enough for the strong force to take over and for them to fuse. In forming the beryllium-7, it kicks out a neutron, and then one forms a lithium-7 by another neutron coming in and kicking out a proton. And so that's what happens in the first 10 seconds of the universe, and then quickly stops. Why does it stop? It stops because the universe has been expanding all this time and is now too cold for the beryllium and lithium atoms to merge and form heavier elements. So one way of seeing this is a chart called the SEG chart, which is one of my favorite charts. It's a chart showing all the isotopes of in this particular case, the lower mass elements. starting off with hydrogen in the bottom. So the vertical axis is protons. The horizontal axis is neutrons. And so what I'm going to go through here is the process of nuclear synthesis from the Big Bang. The thing to note is that the black coloured elements are stable elements, and everything else is unstable. And you might recall that beryllium-8 is very unstable. Okay, so what happens at the beginning of the universe? You start off with a hydrogen atom. A proton comes along and says, "Yep, I'm happy. We'll form deuterium." Then a proton comes along, and you form helium-3. All very good. We're going along the valley of stability. Then another neutron comes along and forms helium-4. Then we see how we have an issue, right? You can't go up or left or right because these elements are unstable. As soon as you try to form them, they will decay. So if I was to add a proton, it says, no, I'm going to go straight back to helium-4. If I add a neutron, it says, no, I'm going to go back to helium-4. So in order to go to proceed, it has to go all the way up to beryllium-7, which is where you've got two helium nuclei merging together, and it kicks out a neutron in this particular case to form beryllium-7. But beryllium-7 is not particularly stable, so it will decay first to lithium-7 by converting a neutron into a proton. And then the reason why things become difficult again is, again, we're in the same situation as we were with helium-4. With lithium-7, if it tries to add a proton, it says, no, this is very unstable, so it'll immediately decay back to lithium-7. And the same, and this, oops, I've gone too far. It drops too many keys. Okay. So when it tries to form beryllium-8, it cannot. And then the universe is now too cold for lithium atoms or helium atoms to merge together to form the heavier elements like boron and carbon. So at the end of the Big Bang, the periodic table looks like this. The universe looks like this. You have neutrons, you have protons, you have deuterium atoms, you have helium nuclei, helium-3, helium-4, and lithium-7. And that's it. You've got no other elements after the Big Bang. And so if nothing else happened, the periodic table would look like this. You'd have hydrogen, which all comes from the Big Bang. You have helium, which mostly comes from the Big Bang. And you have a bit of lithium, which also comes from the Big Bang. Now you'll notice that both helium and lithium have other colors. And so we'll go, in the rest of the talk, we'll talk about where this helium and lithium comes from. So that's 10 seconds after the beginning of the universe, 10 seconds into the Big Bang. About 370,000 years later, the universe is expanded a lot. It's become a lot cooler. And at that point, the protons and electrons can form atoms, and then that releases a photon. And this photon is something that we can actually see and detect. It's called the cosmic microwave background. When these atoms first recombined with electrons, the temperature of the universe was 3000 Kelvin. But since that time, the universe has expanded by a factor of 1,000, or about 1 billion in terms of volume. And so the temperature is now 2.7 Kelvin. And you see this radiation in the millimeter wavelength range. And it's almost a perfect black body. So if you took a spectrum of this and you were to fit a black body curve of 2.7 Kelvin, you'd find that it matches the observations very, very well. But it's not entirely uniform. So here's an image of the cosmic microwave background. And you see that it has little speckles of blue and little speckles of red. These are temperature fluctuations, and they're caused by inhomogeneities in the universe. And as we move time forward, these inhomogeneities grow, and they become the stars and galaxies that we see today. But it takes time for that to happen. And so for a period of something like 200 million years after recombination, which is around 400,000 years after the Big Bang, the universe was dark. There was no stars, there were no galaxies, it was probably quite a boring place. But then something magical happened, and that is stars started to form. And this is an area of very active research, is when the stars formed and how they then reionized the universe, which is something that Dillier touched on in his talk. But all during this time, during the Dark Ages, while there was no stars, the initial temperature fluctuations, which are density fluctuations, were growing with time. So dark matter and not dark energy, but dark matter and gas were falling into these areas of high density, and were then increasing the density enough until one formed stars. And so that's the story of the rest of this periodic table, is how do we go from hydrogen, helium, and lithium to all these different elements. And you see that all these different elements have different colors because there's more than one process which leads to these different elements. And that's what we're going to go through in the rest of the talk. So after the Dark Ages, we got stars. And so here's a lovely image of the Tarantula Nebula. It's something that you can see with your eye. It's a star cluster, many hundreds of thousands of stars in the Large Magellanic Cloud. So if you're in a dark place, Sydney, you probably won't be able to see this, too much light pollution. But if you're in a dark place and you look towards the Large Magellanic Cloud, you'll see a little fuzzy blob. And that's what you, if you get a big telescope, that's what you see. It's just made of millions and millions of stars. In this case, this is a very young cluster. You see the gas that surrounds it, which is the gas from which all these stars were born. So what we're going to do is talk about stellar evolution. And we're going to start by looking at the sun. And here is a diagram which shows how the sun sits relative to all other types of stars. So stars come in all different types of sizes. The sun has one solar mass and sits there in the middle, has a sort of a yellowish orange color. There are many stars which are much more massive, up to 50, 60 solar masses. And there are stars which are much, much smaller, only a few tenths of a solar mass. And this is a diagram which plots all these stars in what's known as the HR diagram, in which you've got luminosity on the left-hand side and temperature on the bottom. So on the left-hand side, you've got brighter stars up towards the top, fainter stars down towards the bottom. And down at the bottom here, you've got hotter stars to the left and cooler stars to the right. So generally speaking, more massive stars are hotter and more luminous, and low mass stars are redder, cooler, and also less luminous. But it's not one-to-one like that because stars do evolve, and we're going to follow the evolution of our sun and see the elements that are created as our sun evolves. So here's our sun. This is a nice picture because it actually shows Venus as it was transiting the surface of the sun. This was taken about, I think it was early 2012 when Venus was transiting the sun. And it gives you just an idea of how big the sun is, because Venus is about the size of the Earth. To give you an idea, the sun is about 300,000 times more massive than the Earth and about 100 times the radius. Now, in the core of the sun, the temperature is very, very hot. Recall that the surface is around 5,000 Kelvin, but the core itself is around 15 million degrees. And so that hot temperature means that the hydrogen atoms, which are stripped of their electrons, are moving around at very high velocity and actually can get close enough to fuse into the heavy elements. And this is what we're going to show you here. It's what's called the PP chain, which I think Matt mentioned earlier. This is what happens. Once the temperature in the core reaches 4 million Kelvin, now recall in the sun has 15 million Kelvin in the core, so this reaction is possible. The velocities of the protons are high enough for them to merge to form a deuterium. Now, in forming deuterium, what's happening is that one of your protons is converting itself into neutron, and in order to keep charge balance, it kicks out what's known as a positron, which is that little white symbol there, and a neutrino. So that's the first step in the PP chain. The second step in the PP chain is you get two atoms of deuterium coming together, and they form helium-3. And to keep the balance, you kick out a neutron, which is the yellow symbol. And then with helium-3, it then collides with another helium-3 atom to form helium-4 and kicks out 2 protons. Now, while it's doing that, it's converting mass into energy, and about 400,000 tons of hydrogen per second are being converted from mass to energy. And our sun is going to do this for about 8 billion years. It doesn't do this forever because eventually it runs out of hydrogen in the core. Another process which occurs not so much in our sun, but in stars which are slightly heavier mass than the sun, so you need a temperature around 15 million Kelvin for this reaction to occur, is the CNO cycle. CNO cycle, it stands for carbon, nitrogen, and oxygen. And it's a cycle because it is a catalytic reaction. And so you start off with your carbon-12 atom, and a proton comes along. It forms nitrogen-13. So we're going from left, so we're going counterclockwise, starting with carbon-12. So it forms nitrogen-13. Nitrogen-13 is radioactive, has a half-life of 10 minutes. So it will then decay by converting one of its protons into a neutron. And so it kicks out a positron and a neutrino, so it becomes carbon-13. Carbon-13 then interacts with another proton, it becomes carbon-14. So you see how the nucleon number increases by 1, but also the element changes from carbon to nitrogen because we've increased the number of protons from 6 to 7. Then a bit later on, another proton comes along and nitrogen-14 becomes oxygen-15. Oxygen-15 is also unstable, has a half-life of 2 minutes. It decays into nitrogen-15. It converts one of its protons into a neutron, kicks out another positron and a neutrino. And then another proton comes along for nitrogen-15, and then you get back to carbon-12 and you kick out the helium nucleus. So you start producing helium through this chain of interaction with carbon, nitrogen, and oxygen. And this is what's called a catalytic reaction, because you're not actually destroying the carbon-12, you're just using that as a way of creating the helium-4 nucleus as you go through this, this particular cycle. So this is a process which can occur in the sun, but the main source of energy in the sun is the PP chain, and this cycle becomes a bit more efficient as you go to higher temperatures. So what happens to our sun when it runs out of hydrogen? Well, here's our sun, a picture of our sun, and I'm going to see if this little graphic works. I'm going to move it to the left here, with Venus in the front here. I'm going to shrink it down in size, and then I'm going to put the Earth here, so it gives you an idea of where the Earth is. So recall that the sun is 300,000 times the mass of the Earth and 100 times the radius. And the Earth is about 150 million kilometers away. What happens when we run out of hydrogen is that the core contracts and starts to heat up, and hydrogen is no longer burning in the core, but is burning in a shell, and this causes the sun to swell up. Now this happens at about 8 billion years. We are 4 billion years into burning the hydrogen in the core. So this is what's going to happen in about 4 billion years from now. Our sun will start to swell up and become a red giant. Unfortunately, it will swallow Mercury, but at this particular stage, it's not going to swallow Venus or the Earth. But you can imagine what this might look like in the sky. You've got something that's going to be 100 times bigger than the size of the sun. When you look up in the sky, the sun subtends an angle of about 0.5 degree. When it's a red giant, the sun's going to subtend an angle of 30 degrees across the sky. Now, of course, what happens is that the sun also becomes brighter. Things on Earth will become very, very hot indeed. So I not imagine that there will be any life on Earth when the sun becomes a red giant. Not great news, but okay, it's still a long way in our future. So here's a sort of a diagram which illustrates what's happening. At the bottom is that yellow star, which is where our sun is today. As it exhausts the hydrogen in the core and starts burning in the hydrogen shell, our sun goes up what's known as the red giant branch. So it decreases in temperature. So it goes from a temperature of about 5,700 Kelvin now to a temperature between 3,000 and 4,000 Kelvin. It also comes a lot brighter. So at the moment you see it's got one solar luminosity. When it gets to the top of the red giant branch, you will see that it has a luminosity of about 1,000 times brighter than it is now. So our sun will becomes cooler, it becomes a lot larger, but it also becomes a lot brighter. So while this is all happening, the core is getting hotter and hotter because the ash from the shell of hydrogen is all contributing to the mass of this core. And then at some point, there's ignition, and our sun goes from what's the tip of the red giant branch, which is there around 3,200 Kelvin and about 300,000 solar luminosities, so 3,000 solar luminosities. It quickly contracts down to what's known as the horizontal branch. And what happens at that particular point is helium ignition. So this is once the temperature of the core of the sun reaches 100 million Kelvin. You get the helium nuclei forming into beryllium. And then beryllium, you recall, is very unstable. So what has to happen is that another helium nuclei has to come in very, very quickly to collide with the beryllium atom while it's still beryllium-8, has not decayed, to form carbon-12. And this is what's called the triple alpha process. And it occurs at first as a very big flash, and then one starts to burn helium. You also start producing oxygen. You get another helium nuclei colliding with a carbon-12 nuclei to form oxygen-16. But again, this only occurs once the temperature of the core reaches 100 million Kelvin. And so this only occurs when the sun is a red giant and there's enough mass in the core of the sun for it to convert helium into first beryllium-8, then carbon-12 and oxygen-16. So what happens to our sun? So when the core ignites, it becomes a star on the horizontal branch, and it actually will shrink. It will shrink a little bit, but it will still be a bit larger. Well, actually, no, it will still quite a bit larger than what it is now, about 10 times the mass of the sun. But at some point, the helium in the core is going to exhaust. So when the sun's on the horizontal branch, it's burning helium in the core, and then it's burning hydrogen in a shell. But at some point, you're going to exhaust all the helium in the core. And so what happens then is you've got helium burning in a shell, you've got hydrogen burning in the shell, and the core consists of carbon and oxygen, which is not fusing into heavy elements. So what happens when you've got things burning in a shell and you've got a degenerate core is your star will swell up. And I've gone too fast. So I have to go through this again. Apologies for finger problems. One other thing that happens at this point of time is that the Earth moves out because the sun has lost a little bit of mass, which is good for us because it means that when it becomes a big giant again, it doesn't actually swallow the Earth. So just to cap where things are, we started off with the main sequence where we've been burning hydrogen in the core. Hydrogen was exhausted. We start going up the red giant branch where you're burning hydrogen in a shell. Then the core becomes hot enough for helium ignition to occur, so the star comes back down to the horizontal branch, so it becomes a little bit fainter, a little bit cooler than when it was on the, a little bit warmer than when it was on the red giant branch. But when it loses, when it's exhausted the helium, it goes back up what's known as asymptotic giant branch. So again, in that particular point, you've got hydrogen burning in a shell, you've got helium burning in a shell, and you go back up the asymptotic giant branch. And so our sun is now an AGB star. And so again, it will swell up. And in fact, it swells up to a size which is about twice the size of when it was with a red giant. The Earth has moved out because our star has lost a fair bit of mass, but it's likely that Venus has probably been swallowed at this point as well. So we've lost the two inner planets to our solar system because our star has become an asymptotic giant branch star. So that then comes up to the asymptotic giant branch star. And then the next step would be to fuse carbon and oxygen into the heavy elements. But this doesn't happen in our sun because our sun is not massive enough. The core of carbon and oxygen, which is left over from the fusing of helium atoms in the shell of helium that's burning, is not massive enough and not heavy enough or hot enough for it to fuse these atoms into heavy elements. So our star goes into what's known as the post-AGB phase. And in this phase, the star is very unstable. It starts losing a lot of its outer shell, and it becomes what's known as a planetary nebula and white dwarf. And I'll just skip that slide and come back to this one. It loses the outer layers of the star, which are mostly helium and hydrogen. And then what's left is a white dwarf, which is a very hot and very dense remnant, and it'll be around 120,000 Kelvin. Now, for most stars of this mass, the star ends its life like that. But in some particular examples, if the white dwarf is a companion to another star, then it still has an interesting future. Going back to this particular curve, well, this has come up good. So this shows the Hertzsprung-Russell diagram again, and on top of that is the path taken by our star, starting off in the main sequence, which is where all stars start off, going up the red giant branch, coming back down, sitting on the horizontal branch when it's burning helium in the core, going up to the asymptotic giant branch when helium is being burnt in the shell, and then to the post-AGB and planetary nebula phase once it ejects the outer layers of the star. And if I was to continue this track further, it will go further to the left and eventually come down to the white dwarf, where it cools it takes a long, long time to cool. And if it's a single object, it's not in a binary system, that's the end of the story for our sun. But for stars which are in binary systems, there's an interesting future ahead. And we'll come back to that in a second once we start talking about supernova. Now, I did want to back up a couple of slides because I do want to talk about a process called the S process, which is another process for creating elements. So let's start off with an iron nucleus, iron 56. So the number of nucleons in this particular atom is 56. And let's assume you've got a source of neutrons. You start adding neutrons to your iron atom with a process called neutron capture. And your iron 56 becomes iron 57. You then add another neutron, iron 57 becomes iron 58. Recall that we're keeping the number of protons constant here, so it's all iron, but the number of nucleons is increasing as we add neutrons. We then add another neutron, so iron 58 becomes iron 59. And then it decays with a process that's called beta decay, because iron 59 is unstable. And it will decay by converting a neutron into a proton and also emitting an electron. That's why it's called beta decay, because you'll see an electron being kicked out, and then that forms cobalt 59. So this is another way to form elements, and this will occur in the envelopes of AGB stars. So when our star becomes an AGB star, it will convert some of these heavier elements, iron, into elements like cobalt. And it's called the S process because it's a slow process. There's also an interesting question here. How can you form iron, or how can you form cobalt when you haven't formed iron in the core of the star? And that's something that we'll come back to in a minute. So it's a little bit of a chicken and egg problem. So in order for you to form cobalt, you already have to have iron in the star. And the answer to that, as you'll see later, is that stars usually are many generations. So you form your iron from larger stars. They distribute the elements into the universe, and then they go into the atmospheres of stars like our sun, where this reaction can take place. But the first stars would not have had any iron, so this process would not have actually occurred. So when you have a planetary nebula, all the outer layers of the star are being expelled into the cosmos, and so the universe starts becoming enriched in carbon and nitrogen, and also the S-process elements. And what's left behind is what's known as a carbon-oxygen white dwarf, because that is the core or the ashes that are left over from the helium burning in the shell. So that's for low mass stars. For high mass stars, things get a lot more interesting. So let's go to a high mass star. And in this diagram, the high mass stars are at the top left-hand corner. So stars of 10 solar masses and above. And stars can be up to 100 solar masses. So that's incredibly bright stars. Of course, such stars have very short lives. They shine brightly, but they don't live very long. And they usually end their lives in a catastrophic fashion. So before we go on to high mass stars, here's a periodic table again with Big Bang and dying low mass stars, so stars like our sun, which lead to planetary nebula. And you see the color coding here. The elements which are in blue and yellow are the ones which are formed in the processes we've just talked about. And so there's quite a few elements here which are not formed in low mass stars or Big Bang. And now we're going to talk about how these elements are formed. So more massive stars. Here we're going to be talking about stars which are more than 10 solar masses in size. So for example, Bellatrix, Spica, Beta Centauri. So when you look at the Southern Cross and you look for the second brightest star, actually it's probably the two pointers. The second brightest star and the two pointers. That's a star which has a mass above 10 solar masses, but doesn't live very long. You see, it only lives for 10 to the 7 years, which is 10 million years, which is not very long at all. And here is our sun down here, and here is the star that we're going to talk about now, Beta Centauri. So what happens with more massive stars? Well, recall that in our sun, at the very beginning, hydrogen gets converted into helium. The hydrogen then becomes exhausted in the core, and the hydrogen then burns in a shell. At some point, the helium ignites, and so you're burning helium in the core and hydrogen in the shell. At some point, you exhaust the helium in the core, so you have hydrogen burning in a shell and helium burning in a shell. And for stars like our sun, that's where things stop, because you don't have enough mass or enough temperature in the core to start burning carbon. But in more massive stars, you'll get carbon ignition. And so you'll start forming the heavy elements. So things like carbon, neon, oxygen, and silicon. But there's a limit to this, and that is when you get to iron. Once you start forming iron and you fuse iron in the core, you no longer gain energy. In fact, you lose energy. And what then happens is that the core contracts. And then we're going to talk about what happens when the core contracts or it actually catastrophically contracts. But to give you an idea of timescales, so imagine this particular star, if you could compress the age of this star in a single year, then it would burn hydrogen on the main sequence until December 7th. So from January 1st to December 7th, it's happily burning hydrogen in the core. Then it would burn helium over the next 24 days. So you can add that together. So December 7th and 24 days gives you to December 31st. Then in the last 42 minutes of the year, so the last 42 minutes before midnight, carbon would burn into the heavy elements. And then neon oxygen would burn in the last several seconds before midnight. And then silicon would be converted into iron in the last 100th of a second of the year. And then there would be quite a New Year's firework display at the stroke of midnight. So what happens when iron when iron starts to form, and you try to fuse iron into heavy elements, you're no longer gaining energy from the fusion process, you're actually losing energy. And so this leads to a catastrophic collapse of the core of the star, which is catastrophic because it accelerates as time goes on. And it then forms what's known as a neutron star, or maybe even a black hole, depending on the initial mass of the star. But what results is in a process that in the outer layers of the star are ejected. Now, it's not entirely clear what causes the outer layers of the star to be ejected. Some people think it's the neutrino flux that comes from forming a neutron star. Others believe there are some hydrodynamical processes which occur once you form the neutron star, because like a little bit of like a bounce. Once you form a neutron star or a black hole, then you get a bounce in the outer layers. So it's not entirely clear, but what does happen is that the outer layers of the ejector, with all these elements, then get ejected out into the cosmos, and these elements will enrich the gas, which then form the stars like our sun. So our star is not a first generation star. It's not known if it's a second or third generation star, but it formed about 4 billion years ago, and the universe is 13 billion years ago. So there were several, at least one generation of star, perhaps several, occurring before the sun started to form. And so that's why you have elements like iron in the atmosphere of the sun, because it's not the first generation star, and so it has already been enriched by previous supernova explosions and previous planetary nebula. So that's what's known as a supernova. In this particular case, it's a type 2 supernova, it enriches the universe with all these different types of elements. And another thing called the R process element, which is what we're going to talk about in a minute. So we talked about S process, this is where you slowly expose elements to neutrons. R stands for rapid, and we're going to go through what R process is now. What's usually left behind after a supernova explosion is a neutron star or a black hole. Now, I'm not going to talk about black holes yet, well, not today, but we're certainly going to talk about neutron stars in a moment. The R process. So the R process stands for rapid, whereas S was slow. And so what happens is that here you've got elements. I've not actually marked a particular example, but you've got neutrons, a large flux of neutrons in which the elements are increasing in the number of nucleons. So if it was iron 56, for example, then it'd be iron 57, iron 58, iron 59, iron 60, and it's absorbing neutrons very, very quickly. Now, in some cases, depending on the actual atom, there may be elements which are very unstable. And so if you were to add a neutron, then it would immediately lose that neutron, unless the neutron flux is high enough and there's another neutron which comes in quickly to go to another isotope of that element which has a higher number of nucleons. So you can see here the number of neutrons is so high that it actually not skips, but goes through an area of the SEG chart where the half-lives of these particular isotopes are very short, but with so many neutrons, it can actually get to an isotope which is semi-stable, which can then beta decay to form an element with a higher atomic number. So this is what's called the R process, and it only works when you've got a high number of neutrons. And these sorts of, in nature, that occurs in type 2 supernova, and another type of cataclysmic event, which we're going to talk about very shortly. So that's the R process. It's another way of forming elements. Okay, just to remind you, S process elements are in the outskirts of AGB stars. To give you an idea of the neutron flux, you've got 1 neutron per 100 years. The R process occurs in supernova, and one other object, which we're going to talk about in a moment, and there you've got a neutron flux of 100 neutrons per second. There's another type of supernova, and it's a supernova related to the white dwarf. So recall that the white dwarf is the end product of our sun. Our sun will become a white dwarf. It'll become a carbon-oxygen white dwarf. White dwarfs have about the mass of the Earth, the mass of the sun, but the size of the Earth. So incredibly dense material. So about 1 million tons per cubic meter. If you took a cubic meter of Earth's soil, it's about 5 tons. So this particular object is much, much more dense. What can happen is that if it's a part of a companion, and that companion goes through, say, a red giant phase, the white dwarf can strip material off the companion and increase its mass. Now, white dwarfs cannot increase their mass indefinitely. At some point, they reach what's known as the Chandrasekhar limit. And when they reach the Chandrasekhar limit, they become a supernova. And this is what's called a type 1a supernova. So here on the left is an artist's impression of what's occurring. you've got your white dwarf there. Around the white dwarf, you've got an accretion disk. That accretion disk is being fed by the companion star as material from the companion star is ripped off, goes into the accretion disk, and the accretion disk then feeds the white dwarf. But the white dwarf can't accrete matter indefinitely. Eventually, it reaches the Chandrasekhar limit, and it then explodes. And in this particular case, you're going to get other elements expelled in the universe. So things like calcium, iron, nickel are expelled in the universe. In this particular explosion, nothing's left behind. In a core collapse supernova, the explosion of a massive star, you end up with a neutron star or a black hole. In this particular case, the white dwarf is completely destroyed, and it takes about a second. So it's incredibly fast. The whole object, which is the size of the Earth and about the mass of the Sun, is destroyed in about a second. And it's so fast because it is so incredibly dense. So here's our periodic table again. We've talked about Big Bang, the blue. We've talked about dying low mass stars, the things yellow. Exploding massive stars in green, and exploding white dwarfs in blue. So now we start filling out the periodic table. You start seeing that we're getting a lot more elements, but we're missing a few. We haven't got the orange colored elements. We haven't got the purple or pink colored elements, and we haven't got the gray colored elements. And for the last 10 minutes, I think, about 8 minutes, so a little bit behind, but not too bad. We're going to talk about how these elements are produced. And we talked about the R process elements, and for many, many years, it was not clear if we understood how we could match the abundance of massive elements. So if I go back to this particular plot here, the R process elements, the R process creates the elements which are colored in orange here. For many, many years, it was not clear if type 2 supernova could produce these elements in sufficient in the abundances that were observed. So things like gold, for example, element number 79, most of that was was produced by R process, but it wasn't clear whether type 2 supernova were sufficient enough to produce the amount of gold that we observe. And that problem had been around for many, many years. It had been theorized that merging neutron stars, so that's neutron stars which are very, very dense, could produce enough R process elements, but no merging neutron star had ever been observed until 2017. So just a few years ago, a kilonova was discovered. So it's a type of a stellar explosion. And this particular kilonova emitted gravitational waves. Gravitational waves had been first observed a year earlier, but this was the first case in which the gravitational wave source could also be observed in the optical. So there was an electromagnetic signature to the gravitational wave event. Now, of course, you need quite a dramatic astrophysical event to form gravitational waves, and you need very dense objects. So, for example, the merging of two black holes or the merging of two neutron stars to generate the gravitational waves that we can detect. And so this particular event generated gravitational waves, and it was also detected in the optical. And perhaps I'll just go through what neutron stars are. We talked a little bit about them, but I think Delia also mentioned them. These are extreme objects. So here's the dimensions, 10 kilometers. They've got the mass of the Earth or even larger. So all that material, all that mass is concentrated into a sphere 10 kilometers across. It's a very exotic matter. Usually the crust of a neutron star consists of atoms, electrons, neutrons, and nuclei. But inside the neutron star, the matter is quite exotic. It could be a neutron superfluid, for example. When you get two of these merging together, you generate gravitational waves. And during that process, because these are neutron stars, you have lots and lots of neutrons. So the neutron flux is very, very high. And so these particular objects are very efficient sources, are very productive in neutrons, and produce a lot of R process elements. And so this was the missing key to understand where the R process elements occurred. So I've got a video next here with a bit of sound. I'm not sure if this will come through, but this is an artist's impression of two merging neutron stars. So one's a bit more massive than the other. What happens when these stars are orbiting each other is that their orbit starts to shrink and starts to get shorter periods because they're emitting gravitational wave radiation. At this early stage, we don't detect the gravity waves, but when just before they merge, they become faster, and so you start seeing the gravity waves, and then they emit, then you start to detect them, and then soon after the gravitational wave event, you've got this high flux of neutrons which convert which create the process elements. And we then see the merger as an optical electromagnetic counterpart. So here's a little video. I apologize if the sound doesn't come through, but I'll speak through this. I'll keep silent while this goes through. So you see them orbiting each other, and they get faster and faster. As they get faster and faster and closer, they start generating gravitational waves that we can detect. That's the blue things. You'll see they'll get much, much faster. At some point they merge, you then get the kilonova, and then you get the R process elements that we see. What's left behind is not entirely clear. It might be a more massive neutron star, or it could be a black hole. In this particular event, people believe it became a black hole. So that forms the R process elements. So to give you an example, in that particular event, about 3 Earth masses of gold were produced. So that's a lot of gold. Don't tell the mining companies, otherwise they might try to go out there and get it. But no, it's a lot of gold. And most of the gold that we have here on Earth are produced from emerging neutron stars, which I just find really, really cool. So periodic table, almost there. We've got 5 of the 7 ways we produce elements, but we are missing a few more. And we're missing both beryllium and boron. So how are they produced? They're produced by cosmic ray fission. So the elements that we see here on Earth, and for boron and beryllium, are not produced by stars or by other astrophysical objects. What happens is that you get cosmic rays interacting with other elements in the Earth's atmosphere to produce the beryllium and boron that we see here on Earth today, because that's the most efficient mechanism for these 2 elements here on Earth. And there's also 2 other elements, technetium and promethium, which I'll talk to you about in a second. They're the last 2 elements to fill out the periodic table. So just to go back to cosmic ray fission, so beryllium and boron and a little bit of lithium are formed by cosmic rays hitting elements in the Earth's atmosphere and forming new elements and new isotopes. A good example is carbon-14. It has a half-life of 5,000 years, 5,700 years. So if there was no mechanism to produce carbon-14, we would not see it. And so carbon-14 is an example of a what's known as a cosmogenic nuclide. It's only produced when a cosmic ray hits another element in the Earth's atmosphere. In this particular case, you've got neutron colliding with nitrogen-14 to produce carbon-14. Unfortunately, it's also produced by nuclear tests. So the last 2 elements I want to talk about are technetium and promethium, because they're very interesting. They're the only 2 elements in the periodic table up to uranium. So uranium is element 92, which don't have any stable isotopes. So all isotopes of these 2 elements are radioactive, which means that even though they are produced by the R process and the OS process, they would have decayed by the time they reach the Earth. And so all the technetium and all the promethium we see on the Earth are produced by radioactive fission. So giving examples, technetium has a half-life of 4 million years, and promethium has a half-life of just 18 years. So the half-life of technetium is only about 1/1000th of the half-life of the age of the Earth. And so these are produced usually by radioactive decay of other elements, things like europium and uranium. And the amount of promethium on the Earth is actually quite small. There's only 0.5 kilo of promethium in the Earth's crust. So it's a very rare element as well, indeed. So our story is now complete. We've gone through the origin of all the elements up to uranium, and I'm happy to take any questions. Thank you very much.
Thank you so much, Chris. I really enjoyed that talk. That really took me beyond just the proton-proton chain and the CNO cycle. If you just look down at the bottom of the Zoom, Chris, there's a bit of a Q&A section, and there's been a few questions that have popped up throughout the talk. Just before we start the Q&A, though, I am aware that it's 11:30, so if you do need to go to lunch, that's fine. But otherwise, if you want to stick around, like I am going to as well, to hear the answers to these questions, you're more than welcome.
Good. So Nalim has a question. What is a positron and a neutrino? A positron is an anti-electron. So it has all the characteristics of an electron, but instead of having a negative charge, it has a positive charge. A neutrino is another very interesting object. It's an object which is thought to have very little mass. It's one of the particles that make up the standard model. There are 3 types of neutrinos. There's electron neutrinos, muon neutrinos, and tau neutrinos. And you see a lot of these neutrinos in chemical reactions. They're very ghostly particles. They don't interact with matter very much. So a neutrino could pass through the Earth without interacting with any of the atoms in the Earth. Very, very ghostly. We see neutrinos from many astronomical events. So, for example, the famous supernova 1987A. The A stands for the fact that it was the first supernova in 1987. It was a supernova in the Large Magellanic Clouds. Those of you who are old, like me, were able to witness this event. It was bright enough to see during the night. It was in the Large Magellanic Cloud. The first indication that there was a supernova occurred was the neutrinos that were detected by a detector in Japan. And they had traveled through the Earth to get to that detector in Japan before they were detected. And these neutrinos arrived a few days before we saw the light of the supernova. So very interesting objects, sources. Good. Where do the neutrons come from to change an element into a radioisotope? So at the neutrons were created during baryogenesis. So at that point in time, neutrons were created along with protons and electrons. In more detail, neutrons and protons are made up of quarks. And I can't recall the exact configuration, but 3 quarks make up a proton and 3 quarks make up a neutron. And they're created right at the very beginning. And they're also created when you have a proton decaying into, or a proton decaying into a positron and a neutrino. Not decaying, but reacting, I should say. Okay, what role does the fundamental particles have in the What role does the fundamental particles have in the PP chain and the CNO cycle? Well, that's a very good question. I think that in this particular case, we see them as decay products. So you wouldn't have the case where you get a positron or a neutrino interacting with an atom and then causing it to convert itself. What happens is that you see these as decay products itself. So their role is in that sense as decay products. Good. Where do neutrons come from for the S process to take place? That's another very good question. So a star would consist of not just the protons, but also neutrons. These are also produced at the beginning of the universe during baryogenesis. So when we think of a star, then we'd have neutrons. But let me go back to the PP chain itself, because I think there's a more complete answer here. And I'll share this slide. I think you can see this, right? Yeah, hopefully you can see this. So actually a lot of the neutrons will come from the first step in the chain. So we start off with 2 protons. They come together, and one of those protons gets converted into a neutron. Okay, and because you need to keep charge balance, you also, some of the decay products are the positron, which is the white circle, and a neutrino. And then when 2 helium atoms, sorry, 2 deuterium atoms come together, they form helium-3, and you kicked out a proton there. You kick out a neutron there. So that's one source of neutrons. Another source of neutrons is the beginning of the universe. There'll be neutrons around. Okay. So a question from Janine. When you say helium burns in the shell, does that mean fusion happens in the shell, or what does that burn mean? So yes, when helium is burning in a shell, the helium atoms are, if I go to the triple alpha process, so these helium atoms are in a shell surrounding the core. The core consists of the ashes of the burnt helium, which is carbon and oxygen. But in that shell, you've still got helium, and the temperature is high enough for those helium atoms to first fuse into beryllium, and then with another helium atom into carbon, and then later oxygen. So yes, helium does burn in a shell, or it fuses in a shell. Okay, we'll keep scrolling down. I hope I'm answering all these questions. So a question from Justine. What did you mean by exotic nuclear matter, and why was the redshift on the X-ray axis one of the first diagrams in the Big Bang? So yes, exotic nuclear matter. This is a very interesting area. So neutron stars are incredibly dense, and you can map it's not clear what actually happens in the central neutron stars, but it's thought that you get the pressures are so high that you form a superfluid, and superfluid is a concept which is results from quantum mechanics, and you can get some very strange behavior of superfluids. So helium, for example, when it's cooled to very low temperatures, becomes a superfluid, and it's exotic because it's not matter that we see from day to day. It's only matter that we see, in these extreme examples. And then the second question was, and why was redshift on the x-axis on one of the first diagrams about the Big Bang? So yes, so I have redshift, but I didn't explain what redshift is, which is a whole talk in itself. So maybe I can do justice in a couple of minutes. So redshift is a measure of the expanding universe. Today we're at redshift 0. If we are at redshift 1, we're looking back in time, the universe was roughly half the size it is today. Well, actually it's exactly half the size of it today, because it defines how much the universe has expanded. So if you look at this diagram, at redshift 100, the universe was 100 times smaller than it is today. So in other words, from that point on to today, the universe is expanded by a factor of 100. And then as you go further back in time, you get a higher redshift. The universe is smaller, and so that's what redshift is. And redshift has a peculiar effect on light. It effectively expands the wavelength of light as the photon propagates through the universe. As the universe is expanding, the wavelength of light increases. So that's what redshift is, and that itself is a whole talk in itself. And then there is a question. Let's see, oops, it's moving up and down as I go. Okay, Gita. So I've heard of brown dwarf stars. What are they, and do they fit into the life cycle of a star? This is an excellent question. So let's go to the HR diagram. So brown dwarf stars, I'm not sure if you see the cursor. I might be able to draw something here. Let me see. Do I have a drawing? It doesn't look like I can draw on this. Anyway, hopefully you see the cursor. So what brown dwarfs live the bottom right-hand corner of the HR diagram. They're very low mass stars, about 1/20th the mass of the sun, so 0.05 solar masses. And they're not large enough for them to burn hydrogen in the core through the PP chain. So they're stars which never actually ignite. They don't have temperatures which are hot enough to cause ignition or burning of hydrogen into the heavy elements. And so another example of a small brown dwarf you can imagine is Jupiter. Jupiter has the mass about 1/1000th the mass of the sun, and it doesn't fuse hydrogen in its core because it's not hot enough, it's not massive enough to generate the temperatures and pressures that you need to fuse hydrogen. And brown dwarfs are just slightly larger versions of Jupiter. Most brown dwarfs have the size of Jupiter, but have much larger masses. So that's what a brown dwarf is. It's a failed star, if you like. A little bit like Jupiter was a failed star. Now, if Jupiter had been a much more massive object, it would eventually started burning hydrogen, and we would be living in a binary system. We would see two stars. We'd see our own sun, and we'd see Jupiter, if it was more massive, burning as well. Okay. Does a black hole have a life cycle? Samantha, that's a fantastic question. It does, in a sense. So black holes are formed. We believe that black holes merge with other black holes to grow. We believe that black holes grow by swallowing stars. So a particular type of astronomical transient is when a star gets too close to a black hole and gets swallowed by the black hole. And we can see some of these events. But black holes also lose mass over time. It's a process called Hawking radiation, and it's got to do with quantum mechanics. The vacuum is not really truly vacuum. You've got particles which appear and disappear all the time. So, for example, you might have an electron and positron appearing in space and then disappearing. This is what's called a quantum fluctuation. If this happens close to a black hole, one particle might be swallowed by the black hole and the other particle escapes. And so this is a mechanism to extract energy from the black hole. And you might recall that energy is mass. And so over time, the black hole loses mass. So in a sense, there is a life for a black hole. It forms and then eventually disappears through this process. Now, it's a very slow process. Black holes lose their mass through what's known as Hawking radiation very, very slowly. And it depends on the mass. The bigger the black hole, the slower the process. The smaller the black hole, the faster the process. But they do have a life, not so much a cycle, but a life. So they appear and then eventually will disappear. Good. Lots of fantastic questions. Hopefully I've been able to answer them.
Well, thank you once again, Chris. I really enjoyed that talk, and I was in the talk last year, and I still feel like I've learned more this year listening to the talk again. And once again, just learning from you the origin of the elements, I really enjoy it. So thank you very much on behalf of everyone that's listening in. We appreciate your time, and yeah, have a great day, Chris.
Thank you very much. Enjoy the rest of the talk in the afternoon. Thanks, everyone.
Thanks, Chris.